So Euclid's algorithm computes the greatest common divisor of two numbers. So we let a and b be integers, and b has to be strictly positive because we're going to divide a by b. So this will compute, Euclid's algorithm computes the greatest, I was thinking about myself, highest common factor, you could say, it's always written, greatest common divisor of these two numbers a and b. The biggest integer that divides them both. And how do you do this? You do this by repeated, Euclid does this by repeated division. So what you do to start with is what we've done before. You take a and you divide it by b, you have an integer quotient q, and you're going to have a remainder, and you can always choose the remainder, as I explained to you, to lie between the remainder r to be between 0, possibly equal to 0 if the division is exact, but always less than b. All the numbers are integers. That's the so-called division algorithm. If you like, you can write that as saying that a divided by b, that's what we're trying to do, is equal to an integer part plus a fractional part, which is r divided by b. And the fractional part is indeed between 0 and 1, strictly less than 1. That's another way of saying the same thing. It's essentially how I explained this. In other words, i.e., the remainder term r is, the quotient, you see, is the integer part of a over b. So the floor of a over b, that's what the quotient is. So r, which is a minus qb, but q is just the integer part, the biggest integer you can fit inside a over b. So that's the floor, what we call the floor of a over b times b. I've sort of said this before, I'm just repeating. That's what the remainder term is. And this is written in computing language, this is written often a percentage b. So for example in C++ or Sage, I'll use that notation to mean this remainder. So it's the positive, it's the non-negative remainder when you divide a by b. And you can test these things yourself on the Keats page with the Sage code. The examples given, and that will help you do some of the exercise. Okay. Now there's a lemma which I'm not going to prove because it's sort of not really part of this course, but it's quite easy. It's 4-line proof in the notes. The greatest common, and I'm not going to define the greatest common divisor, but the greatest common divisor of a and b is equal, when you divide a by b, is the same as the greatest common divisor of b and r. Okay, in other words, if you want to compute the greatest common divisor of a and b, and this is the heart of Euclid's algorithm, you can just convert it to compute, you can just find r, and you'll get a smaller number, and then find the greatest common divisor of b and r, and you just keep going. That's Euclid's algorithm. So perhaps I should say here, the greatest common divisor of a and b means the biggest integer the largest integer that divides them both. We'll do an example in a moment. So in other words, what you do is, so I'm not going to prove this, the proof in the notes. You would have done this last year if you did Euclid's algorithm. So that's the So in other words, what we do is we start with a, and we divide it by b. So we get a quotient, I'll call this q0. And then we get our first remainder, which I call r1. And then we take the b and put it on the left, and we divide b by r1, and we get another quotient, and we get another remainder. And then we keep going. We take the r1, that becomes the number on the left. We try and divide that by r2, and we get a third remainder. And these remainders get less and less and less, because r1 is strictly less than b. This is less than r2 is less than r1. r3 is less than r2. So ri is ri plus 1 is always less than ri. So eventually you get 0. Sorry. Say that again. So I divide a by b. I get remainder r1. I then divide b by r1. I get a remainder r2. I divide r1 by r2, and I get a remainder r3, and eventually the remainder will become 0. So at some point I'll have rn, which is 0, and then I'll have rn minus 2, probably here, is equal to q rn minus 1, rn minus 1, plus the last term, which is now 0. And the greatest common divisor will be this number here. And so if you trace it back, this number, rn minus 1, will certainly divide both a and b. So again, I'm not going to justify this, but then it's easy to see that rn minus 1 is indeed the greatest common divisor of a and b. That's how Euclid's algorithm works. Let's do an example. So, example. Let's just apply this to dividing 93 by 33. So we're going to start with a is equal to, always best to take a bigger than b, although it's not essential, and b equal to 33. So we start 93, we divide 93 by 33, unfortunately it only goes twice. The result is 66. And what's the remainder? 66, 4, 24, 27. It's the first remainder, so that's R1. Then we take the 33 down here, and we divide that by 27. And that goes once. And the remainder is 6. And then we take the 27 down, we divide that by 6, that goes 4 times. The remainder is 3. Take the 6 down, we try and divide it by 3. It goes twice, and then the remainder is 0, so we've finished. And this is the greatest common divisor. So the greatest common divisor of 93 and 33 is equal to 3. Pretty obvious anyway, but that illustrates the method. Just to say how very simple this algorithm is, if you want to, I mean, all computer systems have this built in. You just type GCD or either in lowercase or uppercase in it of 2 numbers, and it will give you the result instantly without telling you what it's doing. But if you want to sort of do something explicit, here would be the code in Sage to actually, I can't write GCD because that already means the internal Euclid's algorithm, so I've called it EUC of A and B. That just is my name for the greatest common divisor using this program. So the idea is that if you're at the bottom step, that's like saying this is the remainder. Actually, you'd go down one more step. So to sort of illustrate this program, I should have continued one more step. So the 3 would have gone down here, and we try and divide that by 0, but of course we can't do anything, so we get stuck here. So the idea is, if you get to the stage where you're evaluating the greatest common divisor of 3 and 0, that means A and B. If B is 0, we know the answer is A. This is just saying that the greatest common divisor of A and 0 is, of course, A, because A divides itself and it divides 0. That's what this is saying. If that's not the case, then we simply replace A and B. This was A and that was B. We simply replace them. A becomes B. So this was A and this was B. On the next line, this is B. And B becomes what was the remainder. This is the remainder. Remember, the remainder is written like this. A percentage B. That's just a fancy way of writing the first remainder. Okay? So it's as simple as that. And eventually you come to a stop. You come to a stop because this remainder will eventually be 0. And then if B is 0, you get the answer A, which will be, the A in this case will be the 3. Okay, so that shows you how simple, in some sense, Euclid's algorithm is. Are there any questions? Now I want to talk about Euclid's extended algorithm. So it's well known the method, this method, if you follow it, this method, also what I've just written above here, this method will show, and I say in general rather than using these numbers, in general, that there exist integers x and y such that the greatest common divisor of two integers a and b can always be expressed as a linear combination with integers of a and b. Okay, there are always integers for which the greatest common divisor is an integer times a plus, one of them will be negative typically, plus an integer times b. And this, if you've done, I don't know if you've done any ring theory, but it's to do with ideals and principal ideals. But I'm going to give you a method for finding, in this case, finding x and y. Okay, is this something you did last year? Okay, so the method I use uses matrices. So let me tell you this. Actually, it was taught to me by a student, so maybe it was taught to him by someone here, I don't know. So you may have seen this method, but I'm going to do the same example. I'm going to find, although it was obvious in this case for 93 and 33, it's obvious that the greatest common divisor is 3. It's not at all obvious what x and y are. So I'm going to find x and y in this case, in the same example. And I'm going to do it as follows. Okay, I enjoy doing this actually with matrices. Okay, so my method might be a variant on one you've seen, is to simply start with the matrix in which you have 93, you have A here, and you have B here. And then you put 1, you put the identity matrix here. And then you just sort of do elementary row operations to correspond to the division. So you just do the division. What we were doing before was we were just looking at the first column. I'm next going to divide 93 by 33. But the point about this method, you've extended the matrix so that this identity matrix sort of memorizes the operations you've done. Okay? So what you do is you just do what I did before. We always start from the smaller number in the first column. So we leave the first row as it is. Sorry, I've done that the wrong way. We leave the second row as it is, I should have said. And we subtract the second row we get the remainder when you subtract the 33 from the 93. So we know that we have to subtract 2 times 33, and that will leave 27. But then you record what you've done here. So 1 minus 2 is still 1, but 0 minus 2 times 1 is minus 2. So this should become a minus 2. So I've changed the first row. And then I say, well, if you run out of space, you can go in any direction. So then I leave the first row as it is. Some people would swap the rows. I don't bother to do that. And then I say, well, to divide 33 by 27, I can only do it once. So that will leave my 6. But I'll have minus 1 here. And I'll have 1 minus 1 minus 1 minus minus 2. That's plus 3. Okay, so I get that matrix. And then I keep going. So I leave the 6 as it is because that's the smallest number. And I divide. I'm just repeating as far as the first column is concerned. I'm repeating what I already did. So we know 27 divided by 6 goes 4 times. That leaves a remainder of... So I'm taking really... What I'm doing is I'm taking the first row. This is not remainder, it's row. The first row minus 4 times the second row. That's what the first row is, and I'm leaving the second row alone. So it's going to be 27 minus 4 sixes, that's 3. 1 minus 4 minus minus 4 is 5. And minus 2 minus 4 times 3 is minus 14. Now, actually, I'm sort of finished, but to make sure I've finished, I do one more operation. So I leave the first row as it is. I know now that 3 goes exactly into 6 2 times, so the remainder is 0. 1, doesn't matter what I write here, to be honest, but I'll just complete it. Minus 1, it's going to get minus 11 there, and I'm going to get 31 there. But as soon as I get the 0, that's telling me that the other number is the greatest common divisor. So when I get to the 0, I know this is the greatest common divisor, and these are the coefficients I need. So this will tell me that 93, the greatest common divisor 3, is equal to 5 times the first number, A, plus, in this case, minus 14 times the second number, which is 33. Okay, the general formula will be the greatest common divisor of A and B will be x times A plus y times B, and this will be x and this will be y. That's basically how